Hello, so welcome back. Today I'll be talking about nucleophilic acyl substitution, which is characterized by this kind of reaction whereby we have a carboxylic acid derivative and there is a substitution of this group directly connected to the carboxyl carbon. So the mechanism for such a substitution is called the addition-elimination mechanism. So the way the mechanism works is that if you observe in the reactant, there's a delta plus carbon over here, which is a site that is attractive to nucleophiles. So the nucleophile attack, and then because the carbon cannot have more than 4 bonds, so one of the bonds have to break, and you will agree with me that the weakest bond over here would be the CO pi bond, because pi bonds are generally weaker than sigma bonds. So the pi bond will break, and this gives us a tetrahedral anionic intermediate over here. And then the next step would be the reformation of the pi bond and the leaving of this leaving group over here. So example would be the hydrolysis of acyl chloride, where X would then be Cl, and then this leaving group will be Cl minus, and the nucleophile would be a water molecule. So let us take a look at how understanding this mechanism help us to understand the reactivity of certain carboxylic acid derivatives. So this is the general scheme of reactivity for carboxylic acid derivatives. So the most reactive is the acid chloride. As we have learned, the acyl chloride is very reactive, especially to reactions like hydrolysis and ester formation. And while the amide is fairly unreactive, right? And so the reason for this we can understand based on the stability of the leaving group. So if the leaving group is more stable, right, then the forward reaction will be more hexagonic, and thus the position of equilibrium will lie more to the right, correct? So if X minus is more stable, the Kc will be greater, right? And so we can understand the reactivity by the stability of the leaving group. So for acid chloride, what's the leaving group? It is Cl minus. For the acid anhydride, it is this carboxylate. For ester, it is alkoxide, and for amide, it is this NH2 minus ion over here. So now how do we compare the stability of the leaving groups? Remember in the previous video, I told you that ARIO method to compare the stability of anionic species. And so we will first take a look at the atom. In this case, Cl minus is the larger atom compared to oxygen and nitrogen, and so it's more able to stabilize the negative charge by dispersing it over its much larger electron cloud. And then we take a look at this too, which is more stable. The atom is the same, but we observe that there is the case of resonance for the carboxylic acid, where there is these two equivalent resonance structures. Therefore, in the true structure of the carboxylate anion, there is sharing of the negative charge over two oxygen atoms, thus dispersing the negative charge and stabilizing the carboxylate ion. And now comparing the alkoxide and the NH2 minus, what do we observe? We observe that they are of the same period, but oxygen is more electronegative. and so it is better able to stabilize or better able to bear the negative charge. And thus the stability decreases and the reactivity thus increases in the opposite direction. But I would like to highlight a second factor that affects the reactivity of the carboxylic acid derivative, and that is resonance. So note that for a carboxylic acid derivative, there is the possibility of this resonance structure. You probably have encountered this before in the amides, right? We learned that the amide, the lone pair on the nitrogen atom, can be delocalized to form a pi bond, and the oxygen has an intensified negative charge. And so let us take a look at the factors determining the extent of resonance. So the extent of resonance depends on the effectiveness of orbital overlap. So note that what is happening over here, an orbital holding the lone pair here overlaps with the pi bond of the CO bond, and so realize that oxygen and carbon are both period 2 elements, and so there's most effective overlap if this orbital over here is of similar size to the period 2 orbitals. So it is most effective when X is a period 2 element. And secondly, it is the second factor is the electronegativity of X. So you agree that if X is more electronegative, it prefers to hold the lone pair towards itself, right? And the lone pair is more difficult to delocalize. Another way to think of it is that if X is more electronegative, it does not bear a positive charge as well. Okay, so this resonance structure will not be that significant. So it's more stable when X is more electropositive. So let us take a look at the extent of resonance. So you will agree that there is the least resonance for the acid chloride. Why? Because the Cl atom is in the orbital of the Cl atom is much more diffuse than the period 2 orbitals of the oxygen and carbon atoms. And comparing the ester and the amide, we realize that the amide has the most resonance because, or perhaps a more accurate term would be that this resonance structure is more contributing, but it is, we'll just say it has the most resonance because the nitrogen atom is less electronegative than the oxygen atom, making this lone pair more available for donation. And thus, now when you compare the acid anhydride and the ester, we observe that for the ester, there's an electron donating R group, and so there's this lone pair is more available for delocalization into the CO bond. And we also observe for the acid anhydride that there's two possible resonance structure, right? You can delocalize into either of the CO pi bonds, and so the extent of the resonance will be smaller. And so because acid chloride has the least resonance and amide has the most resonance, the reactivity increases in this direction, right? Where the least resonance of the acid chloride means that it is the most reactive, or the most resonance in the amide means it is the most stable and the least reactive. And so this brings me to the end of this short video. Thanks for watching.